Hello and welcome to this video on using the null space and the range to determine if a linear transformation is one-to-one or injective and or onto or surjective. If you've heard those words injective and surjective for one-to-one and onto respectively. So in this video I'm going to start off by stating some important results, not going into the proofs of them, but if an important result about the null space and the range of a linear transformation and what that could possibly tell us, about whether or not the transformation is one-to-one or onto. Alright, so I've put up videos before this. Again, I hope you've been following, hope you've been watching. If not, go look for videos on this either from me or somewhere else. I'm going to be assuming you know what the null space and the range of a transformation are. Also what it means for a transformation to be one-to-one and onto. Right, that's all preliminary knowledge that I'm assuming of you if you're watching this video. Okay, so I'll start off with this and then we'll go into some examples, where we find the null space and range of some linear transformation and use it to make statements about whether or not that transformation is one-to-one or onto. So suppose we have a transformation T from vector space V into vector space W, and this is a linear transformation, right? Meaning that this transformation T satisfies the additivity and homogeneity properties, preserves, vector addition and scalar multiplication. Right? Alright, so here's two very important results regarding a linear transformation and the null space and the range of a linear transformation. So T will be one-to-one if and only if, so this again means it goes in both directions, the implications. T will be one-to-one if and only if the null space of T is that vector space with only the zero vector, right, the trivial vector space. Alright. Now again, I'll just kind of say out loud what this means. Remember, T being one-to-one means that there aren't two different values from the domain that go to the same value or map to the same value in the range. Another way of saying that is that every value in the range, every element of the range, has a pre-image with exactly one element of the domain in it. Alright, no more, no less. Alright, then number two, a second major result that you should know. T, a linear transformation will be onto if and only if, again this means it goes in both directions, the range of T is the codomain of the transformation equals, W here is my codomain. Alright, so remember what it means to be onto. Right? Onto simply means that every value of the codomain is in the range. That's exactly what this is saying here. So this is basically the definition of onto. Another way to put it is every element of W, every element of the codomain has a non-empty pre-image, right? That means there's some value, some element of the domain that maps to it. Right. Okay, so what I'm going to do in the following examples, and all my examples in this video are the same, is I'm going to be given a linear transformation, asked to find the null space of that transformation, and the range of that transformation. And if the null space is the set with only the zero vector in it, then I know the transformation is one-to-one. If the null space is not this set, if it has more than just the zero vector in it, because the zero vector will always be in the null space of a linear transformation, then we'll know that the transformation is not one-to-one. And same thing goes for the range. If we determine that the range is the codomain, right, then we will have determined that the transformation is onto. And if we determine that the range is not the codomain, then we'll have determined that the transformation is not onto. Okay. Now I've done this before, as I mentioned at the top of the video. I've found the null space and the range of a transformation before. Remember, I'll do it the long way and also the much shorter way. I'll do it both ways for this first example, but then after that I'm going to kind of stick to using just the standard matrix for a linear transformation to help me. Alright, so here we're asked to determine the null space. Sometimes the null space of a transformation is referred to as the kernel, Kernel there. So you might come across this in some textbooks or some websites if you're looking up stuff. So determine the null space, or the kernel, and the range of the given linear transformation. Right? Now we're given that these transformations are linear, right? So I don't need to check for the additivity or homogeneity properties. They are true. They are holding. Then, after finding these spaces, determine if the transformation is one-to-one and or onto. Alright, so here I have a transformation between R2 and R2, where the rule is this. It takes a vector from R2 with components x, y, sends it to another vector from R2 here with x plus 2y, 3x plus 4y as the components. Alright, so now again, I'll do this the long way and the short way for this first example. So first, let's talk about the null space of T. Now remember the definition of null space, right? The null space in this case would be every vector, say vectors x, from the domain, and this is the domain R2, okay? All the vectors from the domain that map to the 0 vector in the codomain. Alright. So all the vectors from the domain such that their image under T here is the 0 vector in the codomain. Alright, so let's take a look at that equation. So what we're doing basically is solving this equation. So basically, when is the output going to be the 0 vector, right? Say this is my vector x here. Vector x is the one with these components x and y, and I'm trying to figure out what can I replace this vector with to give me a 0 vector output. So t of x on the left there is x plus 2y and 3x plus 4y, and when's this equal to the 0 vector in the codomain, right? The vector with two components of 0. And this leads me, right, to a system of equations, right? In order for these two vectors, these two matrices to be equal, their components have to be equal. So we get this system here where x plus 2y must be equal to 0, and 3x plus 4y must also be equal to 0. And then I could solve this. This is just a two variable system. I could solve this with substitution, elimination. But the way you're probably more familiar by now in this, if you're doing linear algebra stuff, is I write the augmented matrix for this system. Now you could write this as a matrix equation if you want, but I write the augmented matrix for this system, where the coefficients of x down the first column, coefficients of y down the second column, little bar where the equals go, and then the constants over here. Alright, and then I take this augmented matrix and either put it into echelon form and use Gaussian elimination, put it in echelon form, and then solve by back substitution, or put it in reduced echelon form. It's Gauss-Jordan elimination, and you'll have the solutions pretty readily available in reduced echelon form. So I'm going to do that. Alright, put this matrix here into reduced echelon form or reduced row echelon form, which, there's only 2 rows here. And, so I could do this pretty easily by hand. Now, I'm not going to write out the operations. I'm just going to, I'll tell you right now. I know that this left side here, if you were looking at this as the coefficient matrix, right, this 1, 2, 3, 4 here, has a determinant of 4 minus 6 has a determinant of -2, which is not 0. So that's going to be row equivalent to the identity matrix, right? 1, 0, 0, 1. So if you were to perform row operations and put this into reduced echelon form, you'd be getting this here with the 1, 0, 0 first row, 0, 1, 0 second row. And then we're seeing that both x and y are basic variables. And looking left of the bar here, both columns have a pivot, right? Have one of these leading ones with the zeros above and below them. So both x and y are basic, no free variables, right? No free variables. And we're seeing here that there's only one solution then, right? If there's no free variables, there's only one solution. There might be no solutions as well, it depends on the system, but so we're seeing that the value of x, right, this is coefficients of x, coefficients of y, the value of x must be 0. And from the second row, we're seeing that the value of y must be equal to 0. All right. So the only solution to that system, or in this case, the only vector in the null space of the transformation is the 0 vector. All right, so we're seeing here that the null space of T is equal to the set with, just the 0 vector from R2 in it, right? Just the 0 vector from the domain. This is the only vector from the domain that would map to the 0 vector in the codomain. And from my statement on the first page, if the null space of the transformation, a linear transformation, if the null space of a linear transformation is that set with only the 0 vector in it, that tells me that this transformation, this linear transformation, is 1-to-1. Okay, so that means that if you took 2 different inputs, you're always going to get 2 different outputs. All right, no 2 different inputs are going to go to the same output if it's 1-to-1. All right, now that was like, well, again, that was I'd consider that the long way of discussing how to find the null space. And I'll do the long way for the range as well. All right. Now the range, and then I'll talk about the standard matrix and how to use the standard matrix. And again, you should have seen this in my previous videos as well. Now for the range, the way that the range is defined, it's all the outputs, all the possible outputs, so all the values t of x such that x is in the domain. All right, and the domain here is again R2. All right. So it's all the outputs in the codomain such that the inputs came from the domain. And that's a simple way of stating that. So I could very easily just write out here that the range, all right, the range, so in this example, the range of T is equal to the set of vectors that all look like this, right? Every output looks like this, has this form up here. So I write it this way, as all the vectors that look like my output there have that form, as long as this x and y that I'm seeing in here, as long as that those numbers are coming from the reals, right? As long as a vector with those 2 components is coming from the domain. Right. Now this is all well and good, but the question becomes, is this equal to the codomain, right? Is this equal to R2, right? Well, let's see. So let me think of an alternate way here that I could write the range. Now you notice how there's these two variables, these two inputs, x and y, are part of the components of the outputs here. So what I could do is I could take this vector in the that all the outputs look like, and split it up into a sum of two vectors, one involving x and one involving y. And x and y are real numbers, so I could pull those out like like a scalar, when you're reversing scalar multiplication. So I could split this up to x multiplied by the vector with the the coefficients of x, 1, 3 here, plus then y multiplied by the vector with its coefficients 2 and 4. And that's just another way of writing this vector, right? This output vector as x times the vector 1, 3 plus y times the vector 2, 4. And again, as long as x and y are coming from the real numbers here. So what we're seeing is that the range of this particular transformation is made up of all linear combinations, right? This is a linear combination of the vector 1, 3, and 2, 4. So another way to state this, right? Another way to state that the range is the set of all linear combinations of these two vectors is to say that the range is the span of the set with these two vectors in it, with vectors 1, 3 and vector 2, 4. All right. Now look at these two vectors. All right. Now obviously this set spans the range. All right. And the two vectors, there's only two of them, and they are not linear scalar multiples of each other. So remember, when you have a set of two vectors and they're not scalar multiples, then you are linearly independent, right? So this set of vectors spans the range clearly, right? And the set of vectors is independent, so this forms a basis. So the dimension of the range, right? So what we're going to see here is that the dimension of the range is 2, right? Because this range, right? The range is a span, this set with the 1, 3 in it, and the set and the vector 2, 4 in it is a basis for the range. Right, so it has dimension 2. And if the dimension of the range is the same as the dimension of the codomain, well, then they must be the same set. Right. They represent they're isomorphic. Remember, you can set up an this. I'm not saying that this is an isomorphism per se. I mean, we'll see it is in a minute, but if the dimension of the range is equal to the dimension of the codomain, right, which in this case is R2, then the range will be equal to the codomain. All right, it'll be onto. Okay, that little bubble or something. So we're seeing here that this is R2, right? Every vector in R2 can be written as a linear combination. This would be a basis for R2 as well, right? Every vector in R2 would be able to be written as a linear combination of these two vectors, and these two vectors are independent. So yes, we are seeing that the range of this particular linear transformation is the codomain, right? So the range of the transformation is R2. The range is the codomain. Therefore, this linear transformation T is onto. Wonderful, right? And that just means again that every value in the codomain is mapped to by some value in the domain. Wonderful. So now on top of this, we went through this example here. I showed you that, we said, it started off, we said, this is a linear transformation, right? This is a linear transformation. And we're seeing that it's a linear transformation that is both one-to-one and onto. Therefore, this transformation would be called an isomorphism. All right, if you recall that definition, an isomorphism was a linear transformation that was also invertible, meaning both one-to-one and onto. All right. Now that was, like I said, I consider that the long way of going about it. The way I'd prefer, the way I'd usually do something like this, because again, if I was doing a bunch of exercises, I'd want to save a little time. We have a linear transformation here, right? So again, this is OR. Use the standard matrix of the transformation. And I'll be doing this for the rest of the video. If you have a linear transformation, all right, that means that you should be able to represent the transformation as a matrix transformation, meaning I should be able to write the output, see my output vector, as a matrix times the input vector. All right, so I can do that here very easily. Just again, this will be a 2 by 2, the coefficients of the first input variable, the coefficients of x down the first column, 1 and 3, the coefficients of the second input variable down the second column, 2, then 4, and that would be it. And then this matrix multiplied by the input vector, xy, that would indeed give me this output, right? You can go ahead and check and multiply this 2 by 2 times this 2 by 1, and you'll get this 2 by 1. All right, so then what we have here, this 2 by 2 matrix is again the standard matrix for this transformation, and I'll call it A, right? I'll call it A, and we put this into reduced echelon form, or just an echelon form if you'd like. Now I saw this earlier when I was solving that system. All right, this is row equivalent to the identity matrix. Okay. And then you look at this, and we're going to look at certain things. All right. One, right, when we're talking about the null space, right, look for pivot columns. Right, these leading ones. There's a leading one here in the first column. And this, again, these leading ones with zeros below and above and are the pivots, right? Here's another pivot. If every column is a pivot column, right? If every column, which we have here, each column is a pivot column. If every column is a pivot column, then the null space will be only the 0 vector. Then the null space of the transformation will be that set with just the 0 vector in it. All right, and then if not every column is a pivot column, okay, if you have any non-pivot columns, then this is not going to happen. All right. So just keep that in mind. So what we're seeing here is every column is a pivot column. So the null space of the transformation will be only that 0 vector from the domain, right? Only the 0 vector from the domain will map to the 0 vector in the codomain. And remember, if this was the case, if the null space of the transformation was that set with only the 0 vector, then the transformation is going to be 1 to 1. All right, then the second thing to look for is look at the rows, right? So the first one for the null space, and you looked at the columns, looked for pivot columns, and did it have any non-pivot columns? Right? This one didn't. All right, the next thing I'm looking out for is again looking at the rows now. So I look at the rows. If none of the rows are 0 rows, if every row is a non-zero row, right? If every row is a non-zero row, meaning not all zeros, right? Like there's a 1 in that row, there's a 1 in that row. These are non-zero rows. Then the range of the transformation will be equal to that codomain, right? I put W here. Remember, this was the codomain. The range of the transformation will be equal to the codomain. Sorry, of the transformation. Okay. All right. So again, I look at this. I see there aren't any non-zero rows. Now, if there was a row full of zeros, that means that the column vectors, don't span the codomain. Right? The codomain will not be the range. Right? So we are seeing here, hey, none of these every row is non-zero. So the range of T, the range of this transformation, will be the codomain, which was R2. And if that is the case, T is on 2, right? If the range is equal to the codomain. All right, so this is what I'm going to do for the next for the rest of the examples, right? Just quickly go to find the standard matrix for the transformation, put it into an echelon form or reduced echelon form, which I prefer. If you've been watching my videos, I prefer reduced row echelon form because I can have the calculator do it pretty quickly for me. And then is the null space that set with the 0 vector? Basically is asking the same question as, is every column a pivot column? And is the range equal to the codomain? Is it on 2? Is the same as asking, is every row a non-zero row? Right. Okay, so same. So next example. All right, so I've already told you, right? We're told that this is a linear transformation, so I do not need to check, for additivity and homogeneity. All right. Now, if it's linear, like I said before, if it's linear, you should be able to express or represent the output as a matrix multiplied by the input vector. And when these are Euclidean spaces, we keep the vectors the way they are. When they're non-Euclidean spaces, right, not Rn, R2, R3, R4, then we just convert to coordinates, as again you've probably seen if you've been following. So either way, though, we'll be able to express or represent our output as a matrix times our input vector or our input coordinate vector. All right, so this is going to be a 2 by 3 here. This output, I'm going to say down, again, down the first column, coefficients of the first input variable A, 1 then 0. Down the second column, the coefficients of B, -1 then 1. Then the coefficients of C, 2 then 2. And then this matrix multiplied by the input vector ABC there will give me this output. And again, you can double check, take this 2 by 3 times this 3 by 1, you'll get this 2 by 1. All right, so here is our standard matrix. And now I know I said I like reduced echelon form, but look, I mean, all right, well, this would be very, it's already in an echelon form, right? This is already in echelon form here. Because if you look at each row, the first non-zero entry has all zeros below it, right? First non-zero entry has zeros below it. The first non-zero entry, this one has, zeros below it because there's nothing below it. So it's in echelon form. Now, if you could very easily put it into reduced echelon form as well by just adding the second row to the first row. So if I wanted reduced row echelon form or reduced echelon form, it would simply be, that second row would stay the same, and then I'd add, 0 plus 1, 1 plus negative 1, to get zeros above the first non-zero entry in every row as well. And 2 plus 2 is 4. Here's the reduced row echelon form. And then look, right? Pivot, right? This leading non-zero entry with the zeros below and above it. Pivot, the leading non-zero entry with the zeros below and above it. So, not every column is a pivot column. So, the null space of this transformation is not going to only have the zero vector in it. All right. Now I was asked to find the null space. All right. So let's do that. So remember, the null space is I'm trying to find vectors, A, B, C here, such that when I plug in these values, I get the zero vector as an output. So again, now take my reduced echelon form here. Imagine like there's a little bar for the equal signs and then zeros on the other sides. And if you look at our pivots, right, we see that the first two columns are pivot columns. So the first two input variables, A and B, would be basic variables. And then again, the third column is a non-pivot column, so variable C is free. All right, and again, you can leave the free variables the way they look. I personally like to replace them. So I'm going to let C be replaced by T, where T is some real number. I like to replace them with some other parameter, some other expression that can take on any real number value. All right, then from the first row of this, we're seeing that, A plus 4C, or A plus 4T equals 0, meaning A equals negative 4T. I'm just subtracting 4T. And then from this second row, we're seeing that B plus 2C, or 2T, equals 0, so B equals negative 2T. All right, and then so the solutions to this thing, right, if I have the, when is this times this equal to 0, the solutions to that equation, T of what vectors give me the 0 vector, are these A, B, C vectors that I'm plugging in, where A is negative 4 times my choice of T, B is negative 2 times my choice of T, and C is whatever I choose for T. And so do you see how this is just a scalar multiple? T times the vector negative 4, negative 2, and 1. All right, so the null space, the null space of T is the span of the set with just that vector in it, negative 4, negative 2, and 1. Right, every single scalar multiple of that vector belongs to the null space. Right, you plug in any multiple of this vector, you'll get the 0 vector as an output. And again, this is clearly, as I mentioned earlier, right, because you saw that not every column in echelon form or reduced echelon form here was a pivot column. This is not just the 0 vector, right? This is not just the set with the 0 vector. So that tells me that T is not 1-to-1. All right, now this means, right, when I say T is not 1-to-1, remember this means that you should be able to find two different vectors as inputs that go to the same output. And you see right here, 0, 0, 0 would go to the 0 vector, and so would -4, -2, 1. That also goes to the 0 vector, right? Because there are multiple vectors. There's actually infinitely many vectors that would map to the 0 vector. So it's definitely not 1-to-1. Okay. And then again, looking back here, all right, lots of clutter over here now. But now looking back, ignoring these zeros now, looking back at the reduced echelon form, you see that each row is non-zero, right? Each row is non-zero, which is great. That tells me that these column vectors here do span the codomain. Right? So that means that the range is the codomain. Wonderful. All right, so number 2, because I'm seeing that each row in echelon form or reduced echelon form here is non-zero, the range of T is going to be R2. Right? And since the range is the entire codomain, T is onto. Right? That's the definition of being onto. When every value in the codomain is an output, right? When every value in the codomain is mapped to. Great, and it's really as simple as that. All right, I know it might not look simple, but I did this all in the space of one page here. All right, keep going. I'm just doing the same stuff now. So far, every example has been between. I've got 4 examples between Euclidean spaces. R2, R3, R4, R5, whatever. And I have 1 example at the very end that's between some non-Euclidean spaces, but what we're going to do is, as we've done before, is change vectors to their coordinates with respect to the standard basis for the vector spaces. Alright, so again, we are told that this is linear. Alright, this is a linear transformation, so I don't need to check, does the additivity property or homogeneity property hold? They do. So since it's linear, I should be able to express this output vector as a matrix times the input vector. Alright, this is going to be a 3x2 matrix, where down the first column, the coefficients of my first input variable x, so 1, -1, 2. Down the second column, the coefficients of the second input variable y, 3, -3, and 2. And this is multiplied by the input vector, that input with xy there. And again, you can double check, make sure that this 3x2 multiplied by this 2x1 would give me this 3x1. Alright, so here's the standard matrix. Alright, and then I put it into an echelon form. Say again, just going to reduced row echelon form here. Now, I'm hoping you can see that the first row and the second row are just opposites. So all I would need to do is add those, and then I'd have a row of zeros. And remember, in any of the echelon forms, any row of zeros is moved to the bottom. So there'll be a row of zeros. And this leading one up in the upper left hand corner, I'm going to keep that there, and then I would take -2 times this row and add it to this row to give me a 0 down there, and then again I'd be moving the third row to the second row because that row of zeros is moving to the bottom. And then if I do that, -2 times that would be +2 would be 0, -2 times this would be -6 plus this would be -4, so there'd be another pivot position, which I would change that into a 1 and make sure there's zeros above it, right? So I would definitely do this, okay? All right. And again, you can test this out, use your calculator. Now be careful with the calculator. Remember, when there are more rows than columns, you're going to have to add some columns of zeros until they're equal numbers of rows and columns, and then you can put it in reduced row echelon form. Because if you do a matrix, if you try to put a matrix with more rows than columns into reduced echelon form in your calculator, it's going to come back with an error message. So again, just add a column of zeros here to make it a 3 by 3, and just ignore that column of zeros and you'll get this, I promise. All right, so now I look at this thing, pivot, right? These leading ones with zeros below and above them, pivot here. So it looks to me as though each column is a pivot column. So the null space is only the zero vector, right? The only vector that would, from R2, that would map to the zero vector in R3 would be the zero vector. So easy to say that. So the null space here of this transformation is just that set with the, again, this is the zero vector from R2 that would map to the zero vector from R3. And since that is the case, and this is a linear transformation, right? Again, that rule I mentioned earlier, this only applies to linear transformations. This transformation must be 1 to 1. Great. All right. All right, then number 2, looking at this and say, oh, uh-oh. You know, the last couple examples there were all the rows were non-zero. There is a 0 row. That's not good, right? There is a 0 row. All right. So that means that the range is not the codomain. Right? This is not onto, right? This tells me that the range of this transformation is not going to be R3. Right. Now, what will be the range of the transformation? Again, that's pretty simple. The range of the transformation will be the span of the set of vectors that correspond to those the pivot columns. And you know, both columns are pivot columns. So you know, these columns from the original matrix, the vector 1, -1, 2, and the vector 3, -3, 2, right? Just that set of vectors would form a basis for the range. Every value in the range, every output, could be written as a linear combination of these two, and these two are independent. These are not scalar multiples of each other. So the range is the span of this set of vectors, right, made up of all linear combinations of these two, right? And there's only 2 vectors in a basis, not 3, right? Remember, the dimension of R3 was 3, so this is not R3, right? This is not all of R3. So therefore, T is not onto. Right? There are some vectors in R3 that would not get mapped to by this particular transformation. Okay, wonderful. All right, so far we've seen a transformation that's both 1 to 1 and onto, just onto but not 1 to 1, just 1 to 1 but not onto. Probably guess where my next one's going. So I'm gonna guess based on the pattern. I mean, I picked these out, so this is gonna be neither. All right, so here's one from R4 to R4. Ugh. All right, dimension 4 to dimension 4 vector space. So it takes a input from R4 here, you know, a vector with 4 components, and the output is another vector with these 4 components, right? 4 components. So again, this is a linear, right? A linear transformation. So I should be able to express the output vector here as a matrix, and it'll be a 4 by 4, right? It's the dimension of the codomain by the dimension of the domain. That'll be your size, your standard matrix for a transformation, a linear transformation. Down the first column, the coefficients of x1 in these, right? 1, 3, -4, -1. Down the second column, the coefficients of x2, 2, 1, -3, -2. Down the third column, the coefficients of x3, -1, +2, -1, +1. And down the fourth column, the coefficients of x4, 4, -1, -3, and 1. All right, and then multiplied by the input vector, right? That vector that's being input here, x1, x2, x3, x4. And again, you can double check if you wish. Multiply this 4 by 4 times this 4 by 1. Hopefully you get that 4 by 1 matrix back. All right, so here we have our standard matrix, right? This 4 by 4 matrix here. I'll just write standard. All right, and I'm going to have the calculator this time. I'm going to put this into reduced row echelon form, or just a reduced echelon form, right? So I'm going to go to the calculator. I have my 84 plus handy here. All right, come on now. There we go. And then I go to the matrix menu, and then over to edit, and matrix A. Then I'll enter the size first, right? This is a 4 row, 4 column standard matrix, so 4 by 4. And then I just enter all these entries. Okay, so I'm going to pause the video right now and enter these and get back to you, start up again when I have them all entered. Okay, so I've entered my 4 by 4 matrix. Now I'm back in the matrix menu and would like to put this in reduced row echelon form, right? So I go over to the math area. This is in that matrix area, matrix menu again, and scroll until I reach RREF. This is going kind of slow on me here. And don't confuse this with REF. Right? REF is plain echelon form or row echelon form. I want reduced. I mean, it really doesn't matter, but I prefer reduced here. So I hit enter there, reduce row echelon form, and then what matrix, right? So I go back to that matrix menu, and then enter matrix, the A, that 4 by 4 matrix I just entered, and hit enter, and the 4 by 4 in reduced row echelon form should come up, and I will write this. So our first column, 1 with a few zeros, 0, 1, 0, 0, 1, negative 1, 0, 0, and then 0, 0, 1, 0. All right. So now we look at this thing and check out the pivots, right? There's a leading one in one of the rows with the zeros below and above it. There's a leading one in the rows with the zeros below and above it, and there's in the third row has a pivot in it. So the first, second, and fourth column are pivot columns, but not every column is a pivot column. So so again, not every column is a pivot column. That means that the null space of this transformation is not going to be just the 0 vector. All right, there's a free variable here. So I'm going to let my free variable, I'm going to let x3, right? Remember this third column is the non-pivot column. I'm going to let x3 be t, again, where t is just some real number. And if we're finding the null space, remember we're imagining now that there's a bunch of zeros on the other side and equals 0. So from the first row, we're seeing that x1 must be equal to the opposite of t, right? This would be x1 plus t equals 0. Then from the second row, we're seeing that x2 must be equal to t, right? Because it's x2 minus t equals 0, so I'll add t. And then we're seeing that from the last row, that from the third row here, that x4 must be 0, right? x4 must be simply 0. Then this last row would be telling me that 0 equals 0, which is totally fine, right? That is a true statement. There's nothing wrong with that. You just ignore it for now, all right? So the null space, right? The null space, the solutions to that equation. So the solutions to that, when is t of some vector equal to the 0 vector, are looking like this, right? Now every single thing will have a t in it, right? So I'll pull the t out right now and say my vectors x are going to be equal to, pull a t out, and the x1 is negative 1 times t, x2 is 1 times t, x3 is 1 times t, right? x3 is the free variable, and x4 is always 0. Alright, so what we're seeing here is that the null space, right, all the vectors that map to the 0 vector are these multiples of negative 1, 1, 1, 0, right? This vector with 4 components. Alright, so the null space of T is the span of just the set with the vector negative 1, 1, 1, 0 in it. Which is clearly, again, it's not just the 0 vector. Right, so that tells me, again, this is only for linear transformations does this rule really apply. So a linear transformation where the null space isn't just that set with the 0 vector in it, T is not 1-to-1. I mean, I guess it would also apply to any other transformation, right? Because if the null space didn't have just a 0 vector in it, that means you have more than one vector that goes to the 0 vector. You have more than one input that goes to the same output. So yeah, that would apply to any transformation, really. Right. Just not the other way around necessarily, right? Just because you know, if a transformation is not 1-to-1, that doesn't mean the null space is, you know, not the 0 vector in a general transformation. So that's why I'm going to stick to saying we're only dealing with linear transformations here. Okay. 2. Again, looking at the rows now, I'm seeing there's a 0 row in my reduced echelon form here. And that tells me that the range of this transformation is not going to be R4. But again, you can use the pivot columns to help you easily state the range. Right? The range of this transformation is the span, right, of the 3 columns from the original matrix that correspond to these pivot columns. Right, so the first, the second, and the fourth column of the original matrix there, 1, 3, negative 4, negative 1. You know what? There's not a lot of room here, so I'm going to say the range of T is the span of the set with the vectors 1, 3, negative 4, negative 1, the vector 2, 1, negative 3, negative 2, and the other vector, the fourth column, 4, negative 1, negative 3, 1. Right, and this is not R4. It can't be, right? Remember, R4 would have a basis with 4 vectors in it. This only has a basis with 3 vectors in it. It can't be R4. Therefore, T is not onto. Right? So not 1-to-1, not onto. Right? It's neither. So you have seen an example now of linear transformations between Euclidean spaces that are both 1-to-1 and onto, just 1-to-1 but not onto, just 1-to-1 but just onto but not 1-to-1, and neither 1-to-1 or onto. So all 4 possibilities are up there. All right. So my last example. All right, I'm going to be doing the same thing, just we're going to deal with some non-Euclidean spaces. Okay, non-Euclidean spaces. So here I have, again, a linear transformation from the set of 2x2 matrices with real entries to the vector space of 2x2 matrices with real entries. So from R2x2 to R2x2. So remember, and the rule here is T takes, now remember X, my input, is a 2x2 matrix. So X is a 2x2 matrix. The output is some matrix A times X minus the same matrix, the input X times matrix A, where A is this fixed matrix here. A is always this 1, negative 3, negative 1, 4, this 2x2 matrix. All right. Now, don't think you can just pull the A out, or pull the X out. Remember that order matters when you multiply matrices, right? A times X isn't necessarily going to be X times A all the time, right? It could be, but it won't be always. Just remember that matrix multiplication is not commutative. Okay, so remember how we, now again, I'm going to do the same thing where I set up a, it's a linear transformation, so I should be able to express it as a matrix transformation, right? Where I write my output, where I can write this output here as a matrix multiplied by my input vector isn't a vector from Euclidean space, it's a 2 by 2 matrix. So what we're going to do, remember when you have non-Euclidean spaces, is we're going to work with the coordinates with respect to the standard basis, right? So I'm going to have B, I'm going to let B be the standard basis of R 2 by 2. Remember, again, I put this up in other videos. This is dimension 4. So remember, the standard basis has 4 vectors in it, 4 matrices, and they're all those 2 by 2 matrices where exactly one entry is a 1 and the others are zeros. And that'll be for the domain R2 by 2, and then C also is going to be the standard basis. I'll call C the standard basis for 2 by 2 as well, for R2 by 2. But this will be for the, it's not a big deal. They're the same set, right? It's the same set of vectors, so really I could just say B for the whole thing. But so I've got a standard basis for the domain, a standard basis for the range, the codomain, sorry. And then I'm going to change this to its coordinate representation. We're going to translate this into coordinates relative to the standard bases, and then find our standard matrix. All right, so my input. All right, input is some 2 by 2 matrix X. All right, so I'll call this. See this. What does a general input look like? So let's say X is made up of values, say X, Y, Z, and W. Then X, Y, Z, and W can be any real numbers. Right? Now, if I translate that to coordinates, the coordinate vector of X, right, matrix X, with respect to basis B, right, this is from the input set, from the domain, would be, X of that first it would just be X of that first matrix, Y of the second, Z of the third, and W of the fourth. Right, if I wrote them in that order with 1 0 0 0 0 1 0 0 0 0 1 0 and then 0 0 0 1. Okay. Now for the output, right, the output, we have AX minus XA. Now A is this matrix 1 negative 3 negative 1 4, right, multiplied by X, X, Y, Z, W, and it's being subtracted. We're subtracting from that X, X, Y, Z, W, times A, 1 negative 3 negative 1 4. All right, so multiplying these two gives me another 2 by 2, where I have X minus 3Z for the first row, first column, Y minus 3W for the first row, second column, negative X plus 4Z for the second row, first column, and negative Y plus 4W for the second row, second column, and then we're subtracting from this, and then the product of these two would be X minus Y for the first row, first column, negative 3X plus 4Y for the second row, first row, second column, then Z minus W for the second row, first column, and then negative 3Z plus 4W for the second row, second column, and then putting these together. All right, I get this 2 by 2 matrix here. of this minus this. Now the x, if I do that, the x's would cancel, and I'd have positive y minus 3z. So y minus 3z. I'm just putting them in the same order of x, y, z, and w. Then this, that's the first row, first column entries. The first row, second column entries, I subtract them. I would have positive 3x, and then a negative 4y plus a y, negative 3y. And then I have negative 3w, and there's no z's, right? So there's the first row, second column entry. Then the second row, first column entry, I have negative x, there's no x there, negative x. And there's no y's. And z's, I'd have 4z minus z, so plus 3z. And then w's, there's no w there, minus negative w, so plus w. And then finally, the second row, second column entries, there's no x's in either of those. Y's, you have negative y, minus no y's, so negative y. Z's, there's no z there, minus negative 3z would be plus 3z. And then w's, 4w minus 4w, the w's are gone. All right, so here we go. And then I change this to its coordinates, change this to a coordinate vector with respect to the standard basis for the codomain, with respect to the standard basis for R2 by 2. So again, the coordinate vector would look like this. It would be just a 4 by 1, where the first coordinate is this first row. Again, going in the same order I went for the coordinates over here in the input. The first row, first column entry, y minus 3z. And then this first row, second column, 3x minus 3y minus 3w. And then the second row, first column one for the next coordinate, negative x plus 3z plus w, and then the last one, negative y plus 3z. Again, this is with respect to basis c. All right. So the coordinate representation, all right, so the coordinate representation of the transformation, right, this transformation up here. So t of x equals ax minus xa, when written in coordinates, when translated to its coordinate representation, would be t of the coordinates of the input are this 4 by 1 vector here, right, x, y, z, w. Again, this is with respect to basis b, will be equal to, and then the output, whatever ax minus xa is this coordinate vector here, y minus 3z, 3x minus 3y minus 3w, then negative x plus 3z plus w, and then negative y plus 3z. All right, and again, this is with coordinates with respect to the basis, the standard basis for R2 by 2. So now I have it written almost exactly as though we were going from R4 to R4, right? We've taken a transformation between two non-Euclidean vector spaces and written it in such a way, represented it in such a way that it looks like a transformation between Euclidean vector spaces, R4 and R4, right? 4 components each. All right, well, if it's a linear transformation, as they said it was, right, I've already stated that this is linear, I should be able to now express this output as a matrix times my input coordinate vector. Down the first column, the coefficients of x, right, 0, 3, negative 1, and 0. Then the coefficients of y, 1, negative 3, 0, and then negative 1. Then the coefficients of z, negative 3, no z, 3z, right, 3, and then 3. And then the coefficients of w, no w, negative 3w, 1w, and no w, right, multiplied by that input vector, x, y, z, w. Again, this is with respect to the standard basis. All right, so here's my standard matrix for this particular transformation. And as I've been doing, all right, I'm going to write this into in reduced echelon form, right? Reduced row echelon form. All right, so I'm going to pause it again and just go do that in the calculator. You've seen me do it earlier in the video. I'm not going to rehash that. And when I'll pause the recording, and when I come back, it'll be on the calculator. All right, and we're back. And like I said, I put that 4x4 standard matrix in my calculator. Had it do reduced row echelon form for me, and I've written it right here. Right. So what we're seeing, I look for the pivots here, right? The pivots, those leading ones with the zeros above and below them in each row, right? There's that, there's this, and then no pivot in this row, no pivot in this row. So look, only the first column and second column, right, are pivot columns. So that means the null space is not just the zero matrix, right? The zero vector. Now remember my inputs here are 2x2 matrices, right? This was the domain. Right? All right, so we got to find the null space. Right? So remember my variables here were x, y, z, and w, right? These are the coefficients of x, y, z, and w. If I'm going to find the null space, remember you're imagining there's a bunch of zeros over here, like an equal bar, and then a bunch of zeros. All right, so the x and y are basic. And then z, I'm going to replace z with t, and I'm going to replace the other free, these are free, right? Z is free, W is free, because they are, in those columns corresponding to, those non-pivot columns. And I'm going to replace W with, I don't know, R, whatever, right? Just some other expression that represents real numbers. T and R are just real numbers, right? All right, so from that first row, we're seeing that x would have to be equal to 3t plus r, right? Because I'd have x minus 3t minus r equals 0, and then add 3t and add r. Again, this I'm finding the null space. Imagine there's equals 0 over there. From the second row, I'd have y minus 3t equals 0, so y would have to be equal to 3t. Okay, and then and then we have what z is, we have what w is in terms of these free variables t and r. All right, so my solutions, right? Now remember my input in this here. My input were coordinates with respect to a standard basis for our 2x2. So my input x, y, z, w, right? These weren't from the domain, right? This is not from the domain. These are the coordinates of a vector from the domain. We're going to translate it back to a vector from the domain after I'm done. X we saw is again 3t plus r, y is 3t, z is t, w is r, r. And I have two free variables in here, so I should be able to split this up now into the sum of two vectors, one involving t and the other involving r. So hopefully you can see this, right? This is t plus t times, and then down the vector the coefficients of t, 3, 3, 1, 0. And again, these are all coordinates. These should all be coordinates with respect to basis b, right? The standard basis for the domain. Plus, and then r, then down this column here, the coefficients of r, 1, 0, 0, 1. Again, with respect to basis b, right? So what we're seeing here is that, the null space of the matrix, right? The null space of the standard matrix is the span of the set with these two vectors, right? Every vector in the null space of this matrix, the standard matrix, which was this guy, every vector in the null space is a linear combination of these two, right? With 3, 3, 1, 0, and 1, 0, 0, 1. Now, the reason I wrote this is the null space of the matrix is because this is not the null space. This is not the null space of the transformation. It's the null space of the standard matrix, right? Because these columns, again, these columns are from R4, right? These are from R4. My domain vectors are matrices, right? The domain vectors are from R2 by 2, but that's a very simple thing to fix. All I need to do is say, hey, let's translate them back. So I just send them back, make them into vectors, make into vectors from the domain. Right? So the null space of T is the span of, and then remember 3, 3, 1, 0. These are the coordinates of our vectors from the domain with respect to the standard basis. So we have this 3, 3, 1, 0 corresponds to the 2 by 2 matrix where the first row first entry is 3, the first row second column entry is 3, the second row first column entry is 1, and the second row second column entry is 0. 3, 3, 1, 0. And then this 1, 0, 0, 1 corresponds to a 2 by 2 matrix with the entries 1, 0, 0, 1. And there you go. There's the null space of this transformation. Every matrix, right? Every matrix that maps to the 0 vector, every matrix that maps to the 0 matrix is going to be a linear combination of these two matrices here. All right. Now the thing about the null space of this particular transformation, if this is equal to the 0 matrix, that means we have AX is equal to XA. Right? If this is equal to the 0, I just add XA to both sides. We'd have AX equals XA. So what this is here, this is actually the set of all the matrices that commute with A. All matrices X such that AX equals XA, right? Or every matrix in here would be commutative with A. You could multiply them in either order and give you the same result. All right, that's pretty fascinating, right? And again, not every matrix commutes with A, right? But there are infinitely many that do. All right. Now this is not just the 0 matrix, right? This null space. This is clearly not just the set with the 0 matrix in it. All right. Now the 0 matrix is in there, right? It's a vector space. It should be closed under vector addition and scalar multiplication, all that satisfy all those vector space axioms. But it's not just the 0 vector. So that tells me that this particular transformation T is not 1 to 1. All right. So great. So we got the null space for the transformation. Now let's go back. Look at this again was the standard matrix put into reduced row echelon form. Right. And I'm looking here. There are some 0 rows, right? So that means that the range of this transformation will not be equal to the codomain, right? It won't be all of R2 by 2. So that means there's going to be some 2 by 2 matrices out there that don't get mapped to this particular in this particular transformation. But we could say what the range was, right? So let me bring up the standard matrix again. There was the standard matrix, right? Right here. Put it in reduced echelon form. The the pivot columns, remember the pivot columns correspond to columns of the original that form a basis for the range, or a basis for the column space of the standard matrix. So I'm going to write here the column space of the standard matrix. Right. So the column space of the standard matrix, right, is the span of the set with these two vectors in them. 0, 3, -1, 0. And 1, negative, again, the first two columns, 1, -3, 0, 1. All right. Now remember how this corresponds to the range, right? So these what we're going to think of these as are coordinates with respect to that basis for the range, the standard, which is still that same standard basis for R2 by 2. Now this is not the range, but it leads me to the range, right? This is not the range. The column space of the standard matrix is not equal to the range of the transformation unless unless you're dealing with Euclidean space, right? Because these are like Euclidean vectors here. But all we're going to do is change back, right? Change these into vectors that are in the codomain. Right? By thinking about these vectors here as coordinates with respect to the standard basis for the codomain, right? Now the codomain was R2 by 2, so my range should compose of 2 by 2 matrices. Right? So the range of T is actually equal to the span of, and then this, again, this one here, this vector, this coordinate vector corresponds to a 2 by 2 matrix with entries 0, 3, -1, 0 in that order. Right? And then this vector, this coordinate vector, corresponds to a 2 by 2 matrix with entries 1, -3, 0, and 1. Right, so this is this would be the more proper way of writing the range of this transformation. And again, clearly this is not R2 by 2. Remember, the dimension of R2 by 2 was 4. So any basis for R2 by 2 should have 4 vectors in it, 4 matrices. The basis for the range only has 2. Right? The dimension of the range is only 2, or the rank is only 2. So, since the range is not the entire codomain, T is not onto, right? So here's another example of a transformation, a linear transformation, right? Remember, all these were linear. These statements all apply to linear transformations. Here's another linear transformation where it wasn't onto and wasn't one-to-one. So hopefully that made sense with the changing the coordinates, right? Because when you're dealing with non-Euclidean spaces, you have to translate. It'll make it a lot easier for you to just translate things to their coordinates with respect to the standard basis for those non-Euclidean spaces, and then you'll have a transformation, a representation of that transformation that looks exactly like you're having a transformation between Euclidean spaces, and then you work with it the same way I did the first 4 examples. All right, but then you got to remember to translate back. When you're talking about the null space, the vectors in the null space better be the same looking vectors as the vectors from the domain, right? And when you're talking about the range, right, the vectors inside the range had better look exactly the same as the vectors in the codomain. So that's what I mean by, once you get the null space of your standard matrix, think of those as coordinate vectors and just translate them back to vectors of the domain. And once you get the column space of the standard matrix, again, think of those vectors as those will be coordinate vectors. Translate those back so that you get vectors in the range, right? Some vectors that are actually in the codomain of the transformation itself. All right, so lots of stuff to think about there. Like I said, I think it's pretty simple once you get down to finding a standard matrix for a linear transformation, and then putting that standard matrix into an echelon form, whether it be echelon form or reduced echelon form, and then looking for your, is every column a pivot column? If yes, it's going to be one-to-one. If no, it's not going to be one-to-one. And is every row a non-zero row in echelon form? If yes, it's going to be onto. If no, if there is a 0 row, it's not going to be on 2. It's really as simple as that, right, after all this stuff. So I hope you have fun practicing problems of this nature, and thank you for watching.